Hello students, hope you are all doing well. In this video, we will be studying Solution chapter of NCERT Chemistry from class 12. Try to recall what are solutions. They are homogeneous mixture of two or more than two components. Homogeneous mixture. Homo means same. The composition and properties are uniform throughout the mixture. For example, take a glass of water, add a spoonful of salt and stir with the spoon. What happens? Salt dissolves in water and you get a homogeneous solution, isn't it? Why is it a homogeneous solution? Because you have uniform composition throughout the mixture. How many components do we have here? Two, right? Yes, water and salt. A solution which has only two components is called a binary solution. Bi means two. So, binary solution means a solution having two components. Among the different components of a solution, the component that is present in the largest quantity is known as solvent. The other components present in solution other than this solvent are called as solute. Solute is present in smaller quantity. In case of salt solution, which is a solvent then? Yes, correct. Water, right? Since water is present in more quantity, it is solvent. Salt is present in smaller quantity, so salt is solute in case of salt water. In general, when a solute is dissolved in solvent, we get solution. So, solute combined with solvent, we get solution. The salt solution is liquid, right? How do you tell that it is a liquid solution? Is a solution always liquid? No. Let me give you other examples for solution. Consider air. It is a solution because it is a homogeneous mixture of nitrogen, oxygen, hydrogen, carbon dioxide and other gases. Air is in gaseous state. Now consider brass. It is a homogeneous mixture of copper and zinc. Copper and zinc are mixed uniformly to get brass. This is in solid state. Now answering to my question, how we can tell that salt solution is liquid or air is in gaseous state? It is based on solvent. Since water is present in large amount in case of salt solution, so it is in liquid state. So in this unit, we will be considering only binary solution. That is a solution consisting of only two components. So from now onwards, in this unit, wherever I mean to solution, consider that I am speaking about binary solutions. These solutions are classified into three types. They are gaseous solutions, liquid solutions and solid solutions. Can you think of on what basis this classification is done? Absolutely right. It is based on the solvent. When the solvent is a gas, the solution is gaseous solution. And when the solvent is liquid, the solution is liquid solution. When the solvent is solid, the solution is a solid solution. Solute can be either solid, liquid or gas. In a gaseous solution, the solvent is a gas. You can have three different types in case of gaseous solution based on the solute. Gas in gas. Solute here is gas. For example, a mixture of oxygen and nitrogen gases. Liquid in gas. Example is chloroform mixed with nitrogen gas. Chloroform is a liquid solute which is present in gaseous solvent. Third is solid in gas. Example here is camphor in nitrogen gas. Liquid solutions. What are they? Correct. When this solvent is liquid, we call such a solution as liquid solutions. Based on the physical state of solute, we have three types here also. They are gas in liquid, liquid in liquid, solid in liquid. Gas in liquid. Example is oxygen dissolved in water. Do you know? The aquatic life means animals and plants which are living in water, they use dissolved oxygen for their survival. Next type is liquid in liquid. Example is ethanol dissolved in water. Solid in liquid. Example is sugar, salt or glucose that's dissolved in water. Now, if the solvent is solid, what do we call such a solution? Exactly, correct, solid solutions. So, the solutions in which solvent is solid are called as solid solutions. How many variations can be seen here? Again, it is 3. Gas in solid. Example is a solution of hydrogen in palladium. Liquid in solid. Amalgam of mercury with solid. Mercury is a liquid at room temperature. When mercury is mixed with any other metal, it is called as amalgam. Third is solid in solid. Example is copper dissolved in gold. So since pure gold is very soft in nature, it cannot be used to prepare ornaments or jewelries. So a small amount of copper is mixed with gold that is made use in the preparation of ornaments. Now let us try to understand about the concentration of these solutions. Based on the quantities of solute and solvent, we can tell whether a solution is concentrated solution or dilute solution. Concentrated solution, dilute solution. What are these terms? In a solution, if the quantity of solute is relatively large, then it is called as concentrated solution. On the other hand, if the quantity of solute is relatively small, such a solution is called as dilute solution. For example, let us consider salt solution. Take a glass of water, add 1 spoon of salt into it and dissolve. Take another glass of water, add 10 spoonful of salt into it. Now, first one is a dilute solution because the quantity of salt is less compared to that of second glass of water. The second glass of water, to which we have added 10 spoonful of salt, is a concentrated solution. Why? Because the solute is present to a greater extent when we compare it to the first glass of water. Basically, these terms, that is concentrated or diluted solution, gives us an idea about the composition of the components present in a solution in terms of concentration of the solution. If I tell the solution is concentrated or dilute, I am not telling about the exact quantity of components present in it, isn't it? For example, if I tell many students secured 90 plus marks in the examination, can you make out what is the number? No, right? You can't tell. You will be confused. Similar thing with respect to the concentration of solutions. Qualitatively, concentration of solution is told in terms of concentrated or diluted solution. Instead of telling that many students secured 90 plus marks in examination, if I tell 500 students secured 90 plus marks, there won't be any confusion, isn't it? So this is quantitative description. So this quantitative description avoids a lot of confusion. So quantitative description of concentrations gives us a better understanding about the concentration of components in the solution. There are several ways by which we can describe concentration of the solution qualitatively. They are mass percentage, volume percentage, mass by volume percentage, parts per million, mole fraction, molarity and molality. We shall discuss all these one by one. Mass percentage. Here we speak about mass of a component in terms of percentage. Component means it can be solute or solvent that is present in the solution. For any solution, if we want to determine mass percentage of solute, we have to divide mass of the solute by total mass of the solution and multiply it by 100 so as to get the percentage. If we want to determine the mass percentage of solvent, you can calculate it by mass percentage of the solvent is equal to mass of the solvent divided by total mass of the solution into 100. Mass percentage is represented by W by W. The W here represents mass. For example, if I tell 10% solution of glucose in water, how do we know now this is the mass percentage? So we write 10% W by W glucose in water. This means that we dissolve 10 gram of glucose in 90 gram of water to make the solution of 100 gram. Volume percentage tells us about the volume of components of solution in terms of percentage. So for any solution, volume percentage of solute is equal to volume of the solute divided by total volume of the solution into 100. And volume percentage of solvent is equal to volume of the solvent divided by total volume of the solution into 100. Volume percentage is represented as V by V. For example, 10% ethanol solution in water. What does this mean? It tells us that 10 ml of ethanol is dissolved in water such that total volume of the solution is 100 ml. Mass by volume percentage is the mass of the solute dissolved in 100 ml of the solution. Mass by volume is represented as W by V. For example, if I tell 1% W by V glucose solution in water, it means that 1 gram of glucose is dissolved in water to give 100 ml of the solution. This measurement is commonly used in medicine as well as in case of pharmacy. When a solute is present in trace quantity or in minute quantities, we represent concentration in parts per million. It's written as ppm. Parts per million is equal to number of parts of the component divided by total number of parts of all components in the solution into 10 to the power 6. When we speak about percentage, we multiply it by 100. And when we speak about ppm, we multiply by 1 million, that is 10 to the power 6. The pollutants present in atmosphere along with the other gases are in trace quantities. The concentration of these pollutants in atmosphere or in water is represented in terms of microgram per milliliter or in parts per million. Mole fraction is commonly represented by the symbol chi and a subscript is used on the right hand side of the symbol chi to denote the component that we are representing. Mole fraction of a component is equal to number of moles of the component divided by total number of moles of all the components. For example, if we consider a binary solution, let us consider the components as A and B. Number of moles of A and B are represented by Na and Nb. Then the mole fraction of component A is chi A is equal to Na divided by Na plus Nb. Similarly, mole fraction of component B is chi B is equal to Nb divided by Na plus Nb. Also we have chi A plus chi B is equal to 1. That is, sum of all the mole fractions is unity. Molarity is defined as number of moles of solute dissolved in 1 liter of the solution. Molarity is represented by capital letter M. Molarity is equal to moles of solute divided by volume of solution in liters. For example, 0.25 molar. It is represented by capital letter M. So it's also written as mole per liter. So 2.5 molar solution of NaOH. It means that 0.25 moles of NaOH has been dissolved in 1 liter. Molality. Small letter alphabet M is used to represent this term molality. Previously we have studied is molarity and now this is molality. is defined as number of moles of solute per kg of the solvent, and it is expressed as molality is equal to mass of solute divided by mass of solvent in kg. For example, 1 m solution of KCl. So here this m is representing as the molality of the solution. It can also be written as mole per kg. It means that 1 mole of KCl is dissolved in 1 kg of water. There is a difference between molarity and molality, right? What is the difference? We have R in molarity and L in molality, isn't it? The difference is molarity is told in terms of volume of solution and molality is told in terms of mass of solvent. So how we can remember this? Molality, we have L. So let us consider this L stands for liquid, and we will consider this liquid is solvent, right? So when solvent is liquid, we have molality, and therefore in molality we relate the concentration to that of the solvent. So far we have discussed various methods of expressing concentration of solutions. Each method of expressing concentration of the solutions has its own merits as well as demerits. Mass percentage, ppm, mole fraction and molality are independent of temperature, whereas molarity is temperature dependent. This is because volume depends on temperature and mass percentage, mole fraction, molality are expressed in terms of masses, and therefore this mass is independent of temperature, and that's why mass percentage, ppm and molality are independent of temperature. So when we perform any experiment, which concentration that we should be choosing to express the concentration of components? So we have to choose concentrations in such a way that depending on the experimental conditions. When we perform an experiment which is not affected by temperature, we can express concentrations in molarity. And when the experimental values or the experiment itself is depending on temperature, we can express concentrations in terms of molality, mass percentage or in terms of ppm. Let us see a few examples on how we can determine concentrations of solutions. First example, 4.8 gram of NaOH is dissolved in 120 gram of water. Calculate mass percentage of the solution obtained. So we are given with mass of sodium hydroxide as well as water, and we are preparing a solution by dissolving that sodium hydroxide in water. We have mass of sodium hydroxide, that is solute, which is equal to 4.8 grams. Also it's given mass of water, which is solvent, 120 grams. We should find mass percentage of the solution that is obtained. Since they have asked for mass percentage of solution, as the solution is containing solute as well as solvent, we need to calculate mass percentage of solute as well as mass percentage of solvent. We have the formula: mass percentage of solute is equal to mass of solute divided by mass of solution into 100. I'll write this as equation 1. Similarly, mass percentage of solvent is equal to mass of solvent divided by mass of solution into 100. I'll write this as equation 2. So we know mass of solute and mass of solvent, that's given to us. It's 4.8 gram and 120 gram respectively. We need to calculate mass of solution. This is equal to sum of masses of solute and solvent. So it's mass of solute plus mass of solvent. Mass of solute is 4.8 grams. Mass of solvent is 120 grams. So therefore, mass of solution is 124.8 grams. So now let us substitute these values into equation 1 and 2 to find mass of solute. So from 1, I can write mass percentage of solute is equal to mass of solute, that's 4.8 gram, divided by mass of solution, which is 124.8 grams, into 100. So gram and gram gets cancels with one another. After simplifying, we get the answer as 3.85%. So now we need to determine mass percentage of solvent. So that is very simple to calculate. So the total percentage when you consider the solution is 100. So we can subtract mass percentage of solute from the 100 to get mass percentage of solvent. So here instead of formula 2, I can also write the formula as mass percentage of solvent is equal to 100 minus mass percentage of solute. So writing that mass percentage of solvent is equal to 100 minus mass percentage of solute. So this is equal to 100 minus 3.85%, which is equal to 96.15%. So therefore, for the solution which is obtained by dissolving sodium hydroxide in water, mass percentage of solute is 3.85% and mass percentage of solvent is 96.15%. Example 2. Calculate the molarity of a solution containing 5 gram of sodium hydroxide in 250 ml solution. So let me write the formula for molarity. So we have molarity. It is the number of moles of solute dissolved in 1 liter of the solution. So therefore the formula is moles of solute divided by volume of solution in liters. Let us write what are the things that's given in the question. So they have given us mass of sodium hydroxide, mass of NaOH, they have given it as 5 gram. Also they have given us, we have 250 ml solution. So it is volume of solution, it's given to us, that is 250 milliliters. So now this volume of solution should be in liter to substitute into the formula for molarity. So dividing this by 1000, we will get molarity in terms of liter. So that is 0.25 liters. We need to calculate number of moles of sodium hydroxide. So moles of NaOH is equal to its mass divided by molar mass. So it is 5 gram divided by molar mass of sodium hydroxide is 40 gram per ml. Gram and gram gets cancelled. Dividing 5 by 40, the answer comes out to be 0.125 moles. Now let us substitute all these values into the formula for molarity. And therefore, we have molarity is equal to mass of solute, that is 0.125 mole divided by volume of solution in liter, which is 0.25 liter. Simplifying this, we get 0.5. The unit is mole per liter, or the same can be written as 0.5 molar. So therefore, the molarity of solution containing 5 gram of sodium hydroxide in 250 ml solution is 0.5 molar. Example 3. If the density of some lake water is 1.25 gram per ml and contains 92 gram of Na plus ions per kg of water, calculate the molality of Na plus ions in the lake. So let us write the formula for molality, which is number of moles of solute dissolved in 1 kg of solvent. So therefore, the formula is moles of solute divided by weight of solvent in kg. So here we need to find out number of moles of solute to substitute into the formula for molality. So they have given us density of water, which is equal to 1.25 gram per ml. Weight of Na plus ions has been given. Weight of Na plus ions is equal to 92 grams. So they have given it's 92 grams per kg of water. So therefore weight of water, which is solvent, that is 1 kg. So we need to calculate is moles of solute. So moles of Na plus is equal to its mass by atomic mass, which is equal to 92 grams divided by 23 grams per mole, which is equal to 92 divided by 23, it's equal to 4 moles. So let's substitute into this formula. So molality, it's equal to moles of solute, which is 4 mole, divided by volume of solvent in kg. So here it's water, 1 kg. So therefore molality is 4. It is 4 mole per kg or 4 molal. Now we shall consider a situation. Take a glass of water in your hand. Add 1 spoon of salt into it. Dissolve. What you are going to get by doing this? Salt solution. Am I right? Here salt is a solute and water is solvent. Add another spoon of salt. Dissolve it. Go on like this. At certain stage, the salt will not be dissolved further. It will settle in the bottom. Am I right? Go check out this immediately. From this, we can tell that there is certain specific amount of solute that can be dissolved in specific amount of solvent. And this is what we term as solubility. So solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent at a specified temperature. Solubility depends upon the nature of solute and solvent. It also depends on temperature as well as pressure. Let us see how temperature and pressure affect solution of a solid or a gas in liquid. Firstly, we shall consider the solubility of a solid in a liquid. Important thing you should note here is that every solid does not dissolve in a given liquid. For example, let us consider sodium chloride and sugar. So these two compounds, that is sodium chloride and sugar, dissolve easily in water. Consider naphthalene and anthracene. They do not dissolve in water. On the other hand, the naphthalene as well as anthracene dissolves readily in benzene, but sodium chloride and sugar do not dissolve in benzene. How do we know whether a solute can be dissolved in a given solvent? In general, a solute dissolves in a solvent if the intermolecular interactions are similar in both the solute and solvent. Or we can tell that like dissolves like. That is, polar solutes dissolve in polar solvents and non-polar solutes dissolve in non-polar solvents. When a solid solute is added to the solvent, some solute dissolves, and as the solute dissolves, its concentration increases in the solution. This process is known as dissolution. Some solute particles in the solution collide with the other solid solute particles and get separated out of the solution. This process is known as crystallization. After some time, the two processes, that is the dissolution and crystallization, occurs at the same rate. At this stage, the number of solute particles going into the solution is equal to the number of solute particles that is separating out of the solution. And this creates a state of dynamic equilibrium in the system. At this equilibrium stage, the concentration of solute in the solution will remain constant under the given condition. That is, at a given temperature and pressure, the concentration of solute at this equilibrium state will remain same. The similar process is taking place when gases are dissolved in liquid solvents. Now, for this solution, if we add more solute, it cannot be dissolved at the same temperature and pressure. Such a solution is called as saturated solution. On the other hand, if you can dissolve more solute in a solution at the same temperature and pressure, we call such a solution as unsaturated solution. So to define, an unsaturated solution is the one in which more solute can be dissolved at the same temperature and pressure. The solution which is in dynamic equilibrium with undissolved solute is the saturated solution and contains maximum amount of solute dissolved in a given amount of solvent. So, solubility of this saturated solution is equal to the concentration of the solute. We have already studied that solubility of one substance into other depends on the nature of the substance. In addition to these variables, two other parameters, that is temperature and pressure, also controls the solubility of one substance in another. Temperature changes significantly affects the solubility of a solid in a liquid. If we consider the equilibrium between solute, solvent and the solution. So this equilibrium is represented by the equation here. As this is a dynamic equilibrium, it must follow Le-Chatelier's principle. In general, for a saturated solution, if the dissolution process is endothermic, that is, if heat is given to the system during dissolution, delta H of solution is greater than 0 in this case. The solubility increases with the increase in temperature. And if the dissolution process is exothermic, that is, if heat is given out during the dissolution, delta H of solution is less than 0 in this case. The solubility will decrease with increase in temperature. this was found true experimentally as well. We know that solids and liquids are highly incompressible and practically they remain unaffected by changes in pressure. As a result, pressure does not have any significant effect on solubility of solids in liquid. The process of dissolving a gas in a liquid solvent is similar to that of a solid in liquid solvent, which we have discussed just now. Have you ever wondered that how aquatic plants and animals get oxygen for their survival? It is the oxygen that is dissolved to a small extent in water that sustains all aquatic life. Many of the gases dissolve in water. Hydrogen chloride gas is highly soluble in water. Why there is a difference in solubility of different gases in water? Solubility of gases in liquids is affected by pressure and temperature to a great extent. The solubility of gases increases with increase in pressure. Let us try to understand this effect of pressure considering a situation. Let us consider a system as shown in the figure here for solution of gases in a solvent. The lower part is solution and the upper part is gaseous system at a pressure P and temperature T. Let us assume that this system is in a state of dynamic equilibrium. That is, in this system, rate of gaseous particles entering and leaving the solution phase is the same. Now, let us increase pressure over the solution phase by compressing the gas to a smaller volume. Now, this compression increases the number of gaseous particles present in unit volume over the solution. And also, it increases the rate at which gaseous particles are striking the surfaces of the solution to enter it. The solubility of gas will increase until a new equilibrium is reached. Now, this results in an increase in the pressure of a gas above the solution and thus solubility of gas increases. The first quantitative relation between pressure and solubility of a gas in a solvent was given by Henry, which is known as Henry's law. This law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution. At the same time, Dalton independently told that the solubility of a gas in a liquid solution is a function of partial pressure of the gas. Now, if we use the mole fraction of a gas in the solution as a measure of solubility, then we can tell that the mole fraction of gas in the solution is directly proportional to partial pressure of the gas over the solution. The most commonly used form of Henry's law states that the partial pressure of the gas in vapor phase is proportional to mole fraction of the gas in the solution. That is, partial pressure P is directly proportional to the mole fraction chi. So mathematically, Henry's law is written as P is equal to Kh into chi, where Kh is Henry's law constant. According to this mathematical equation, when we plot a graph of partial pressure of the gas versus mole fraction of the gas in a solution, we should get a straight line that is passing through the origin. Different gases have different values of Henry's law constant at the same temperature. So you can check out these values from the table here. So this table tells us that Henry's law constant is a function of nature of the gas. And from the mathematical expression of Henry's law, we can tell that higher the value of Henry's law constant at a given pressure, lower is the solubility of the gas in that particular liquid. From the table, we can see that the value of Henry's law constant Kh for both nitrogen and oxygen gases increases with increase in temperature. This indicates that the solubility of nitrogen and oxygen gas increases with decrease in the temperature. So it's due to this reason that the aquatic species are more comfortable in cold water rather than in warm waters. Consider an example. Henry's law constant for the solubility of methane in benzene at 298 Kelvin is 4.27 into 10 to the power 5 mmHg. Calculate the solubility of methane in benzene at 298 Kelvin under 760 mmHg. So we have Henry's law given by, so the mathematical representation is P is equal to KH into chi, where P is the partial pressure, KH is Henry's law constant, chi is the mole fraction. So in the question they have given us that Henry's law constant, which is KH, is equal to 4.27 into 10 to the power 5 mmHg. Calculate solubility of methane in benzene at 298 Kelvin under 760 mmHg. So the pressure P is given. It is 760 mmHg. So we need to calculate solubility. So here solubility is given in terms of mole fraction chi. So rearranging the mathematical expression for Henry's law constant, I can write chi is equal to P divided by KH. Substituting the values, P is 760 mmHg. Henry's law constant is 4.27 into 10 to the power 5 mmHg. Simplifying, 760 divided by 4.27 is equal to 177.98 into 10 to the power minus 5. So this can be approximately written as 178 into 10 to the power minus 5. So this is the mole fraction of methane in benzene at 298 Kelvin. Aquatic life need oxygen dissolved in water for their survival. In warm water, less oxygen is dissolved, and as a result, survival of aquatic life is difficult. In cold water, oxygen will be dissolved more, and aquatic life will get oxygen required for their survival. Now, let us discuss the application of solubility of gases in liquid. It has several applications in industry, and it also explains certain biological phenomena. We see such an application in cold drinks and soda water. When we open the sealed lid of cold drinks or soda water bottle, we see bubbles that are coming out of it. Let me consider soda water. Carbon dioxide gas is dissolved in water under high pressure. High pressure is applied to increase the solubility of carbon dioxide. So, when we observe the sealed bottles of cold drinks or soda water, we do not see carbon dioxide and water as separate. But when we open the bottle, pressure inside the bottle will decrease. When pressure decreases, solubility of gas also decreases. As solubility decreases, carbon dioxide comes out in the form of bubbles. That is why we see bubbles coming out of soda water. These bubbles are the bubbles of carbon dioxide gas. Another example is related to scuba divers. When the scuba divers goes inside water, pressure underwater will be more than the pressure at the surface. This high pressure would lead to the collapse of internal organs. So because of this high pressure, the internal organs of scuba divers will be collapsed. So in order to avoid this, these scuba divers carry a cylinder with air under high pressure for breathing, so as to balance the pressure inside the body as well as the pressure outside the body underwater. Many gases like oxygen and nitrogen which are present in air will be dissolved in blood due to this high pressure that is present. When these scuba divers come to the surface, what happens is that the pressure will slowly decrease. When the pressure decreases, solubility of dissolved gases will also decrease. Oxygen, which is dissolved in blood, will be used for many of the metabolic processes. But nitrogen? So, as the scuba divers comes up to the surface, solubility of nitrogen will decrease and these nitrogens will be coming out of the blood as bubbles. This is very, very dangerous. These nitrogen bubbles blocks blood capillaries. This medical condition is known as bends, and this would be the life-threatening for human being. To avoid bends as well as the toxic effect of high concentrations of nitrogen in the blood, the tanks used by scuba divers are filled with air diluted with helium. This decreases the concentration of nitrogen in air. At high altitudes, the partial pressure of oxygen is less than that at the ground level. Due to this, concentration of oxygen in the blood and tissues of people who are living at high altitudes or mountain climbers will be very low. Low blood oxygen causes climbers to become weak and they are unable to think clearly. This condition is what we call as anoxia. Now, if we ask a question, how temperature will affect the solubility of gases in liquids? The answer is solubility of gases in liquids decreases with increase in temperature. When dissolved, these gas molecules are present in liquid phase. So, we can consider the process of dissolution of gas in liquid is similar to that of condensation process. Heat is liberated in this process, means the process is exothermic in nature. We have just studied that dissolution process involves dynamic equilibrium and therefore it must follow Le Chatelier's principle. Since the dissolution process is an exothermic process, the solubility of the gas decreases with increase in the temperature. Now, let us study about the vapor pressure. We will be discussing about vapor pressure of liquid solutions, especially the vapor pressure in case of liquid in liquid solutions and solid in liquid solutions. Can you tell me what liquid solutions are? Exactly. The solutions in which solvent is liquid is called as liquid solution. So, solute here can be a solid, liquid, or it can be a gas. Here, generally, the liquid solvent is volatile and the solute may be volatile or it may not be. Volatile substances are those which get easily evaporated when heated. For example, petrol, kerosene, ether, etc. On the other hand, when you heat the substances, if it do not evaporate easily, are called as non-volatile substances. For example, if you take sugar and you heat it, it will not evaporate. So, sugar is an example for non-volatile substance. Let us discuss about the vapor pressure in case of liquid in liquid solutions. Don't forget that we will be discussing only about binary solutions. So, the solutions that are having only two components. We are going to study about the vapor pressure. So, we need to know what this vapor pressure is. It is the pressure exerted by the vapor present above a liquid surface. For example, if you take water in a container and heat it, water will be converted into vapors and escape into atmosphere. These vapors cannot exert any pressure on the liquid because they escape into atmosphere. Now, if we close the container with a lid, the vapors cannot escape. and they will exert a pressure on the liquid present below them. This pressure exerted by the vapors is what we call as vapor pressure. I told you that the molecules undergo vaporization. Can you tell me which molecules are undergoing vaporization? It is the surface molecules that are undergoing evaporation because they have high energy and are bound to less number of surrounding molecules compared to those molecules of water which are present inside. So, always remember, it is the surface molecules that will be vaporized in any liquid. As you continue heating, the molecules from interior of the liquid will gain energy and move to the surface, and these molecules undergo vaporization, and this process continues. Now, let us consider a binary solution of two volatile liquids in a closed vessel. Why it is volatile liquids? Because only volatile liquids will be converted into vapor form. Only when the liquid is converted into vapor form, it will exert vapor pressure, right? Let us denote the two components as 1 and 2. Since the components are volatile, when heated, they evaporate. When heated, these liquids will be converted into vapor and vapors condensed to form liquid again. So, there is a dynamic equilibrium between the vapor phase as well as the liquid phase. Let us consider the total vapor pressure at equilibrium stage as P total and P1, P2 be the partial vapor pressures of two components 1 and 2 respectively. These partial pressures P1 and P2 are related to the mole fractions chi1 and chi2 of the two components 1 and 2 respectively. How they are related? The relationship is given by French chemist F.M. Raoult. The relationship is known as Raoult's law, which states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in solution. So, for component 1, P1 is directly proportional to chi1. By removing the proportionality symbol, we can introduce a constant and we can write the expression as P1 is equal to P1 naught into chi1, where P1 naught is the vapor pressure of pure component 1 at the same temperature. Similarly, for component 2, we can write P2 is equal to P2 naught into chi2, where P2 naught represents vapor pressure of the pure component 2. According to Dalton's law of partial pressure, we can write the total pressure, that is P total, over the solution phase in the container as sum of the partial pressures of the components of the solution. That is, we can write P total is equal to P1 plus P2. If we substitute the values of P1 and P2 from Raoult's law into the equation obtained from Dalton's law, we get P total is equal to chi1 P1 naught plus chi2 P2 naught. Now we will write the mole fraction of component 1 in terms of component 2. So, P total will be equal to 1 minus chi2 into P1 naught plus chi2 into P2 naught. Now you might ask, can't we write chi2 as 1 minus chi1? Of course you can write it. After simplifying, we get P total is equal to P1 naught plus P2 naught minus P1 naught into chi2. What you can tell about the relationship between total pressure, partial pressures of pure components and mole fraction of component by looking into this expression. Try to figure out what information does this equation give. So, we can tell that equation relates total vapor pressure over the solution to the mole fraction of any one component. Secondly, the equation tells us total vapor pressure over the solution varies linearly with the mole fraction of component 2. Third, we can also tell that depending on the vapor pressure of pure components 1 and 2, total vapor pressure over the solution can decrease or increase with the increase of mole fraction of component 2. If we plot a graph of P1 or P2 versus mole fractions chi1 and chi2 for a solution, we get a straight line graph as shown here. These lines 1 and 2 pass through the points for which chi1 and chi2 are equal to unity. Similarly, in the plot, line 3 of P total versus chi2 is also linear. The minimum value of P total is P1 naught and the maximum value is P2 naught. Assuming that component 1 is less volatile than component 2, that is P1 naught is less than P2 naught. Now, if we know partial pressures of the components, we can determine the composition of vapor phase in equilibrium with the solution. That is, if we want to know the mole fraction of the volatile components which has been converted to vapor phase above the solution. If Y1 and Y2 are the mole fractions of the components 1 and 2 in the vapor phase, we can make use of Dalton's law of partial pressure here. Y1 is equal to P1 divided by P total and Y2 is equal to P2 divided by P total. According to Raoult's law, the vapor pressure of a volatile component in a given solution is Pi is equal to chi Pi naught. According to Henry's law, the partial pressure of gas in vapor phase is proportional to mole fraction of the gas in the solution. That is, P is equal to Kh into chi. If we compare these two equations for Raoult's law and for Henry's law, we can see that the partial pressure of volatile component or gas is directly proportional to its mole fraction in solution. The difference we observe is only with respect to the proportionality constant Kh and P1 naught. Kh differs from P1 naught, and when Kh becomes equal to P1 naught, the mathematical expressions for Raoult's law as well as Henry's law becomes equal. So, we can tell that Raoult's law is a special case of Henry's law. Now, let us discuss about another important class of solutions. Solids dissolved in liquids. Can you think of a few examples for solids dissolved in liquid? Sodium chloride, glucose, urea and cane sugar in water, iodine and sulfur dissolved in carbon disulfides are a few examples. If we speak about the physical properties of these solutions, a few properties are quite different from those of pure solvents. For example, let us consider vapor pressure. Do you remember that what is vapor pressure? Liquid will be vaporized at a given temperature and these vapors will exert pressure on the liquid phase. And when there is an equilibrium between the vapor phase and liquid phase, the pressure exerted by the vapors of the liquid over the liquid phase is what we call as vapor pressure. From the image, you can see that we have pure solvent and the molecules are undergoing evaporation. Can you tell me which molecules are undergoing evaporation? It is the surface molecules that are undergoing evaporation. In a pure liquid, the entire surface is occupied by molecules of the liquid. Now, if we add a non-volatile solute to a solvent to give a solution. The vapor pressure in this case is dependent only on the solvent because we are adding a non-volatile solute. Now the question is whether vapor pressure of the solution at the given temperature will be same as that of pure solvent or not. Can you just think what happens to the vapor pressure? Will it increase? Will it decrease? Or will it remain same? The answer is the vapor pressure of the solution at a given temperature will be lower than the vapor pressure of the pure solvent at the same temperature. Why would the vapor pressure decrease? You know that the molecules present on the surface will undergo evaporation. In the solution, the surface has both solute and solvent molecules, isn't it? By this, the number of solvent molecules which are present in the surface becomes less. As a result, the number of solvent molecules escaping from the surface is correspondingly reduced. When less number of solvent molecules undergoes evaporation, obviously the vapor pressure also reduced. And this is how you can explain the decrease in the vapor pressure of pure solvent when we add non-volatile solute. Now, suddenly you will think, how much decrease would be observed in the vapor pressure of a pure solvent when we add a non-volatile solute? This decrease in the vapor pressure of solvent depends on the quantity of non-volatile solute which are present in the solution, and this does not depend on the nature of the solute particles which are added. Example for this is the decrease in vapor pressure of water by adding 1 mole of sucrose to 1 kg of water is nearly similar to that of the decrease in vapor pressure produced by adding 1 mole of urea to the same quantity of water at the same temperature. We can use Raoult's law here. What does Raoult's law tell? Can you just state Raoult's law? For any solution, the partial pressure of each volatile component in the solution is directly proportional to its mole fraction. In a binary solution, let us denote the solvent by 1 and solute by 2. When the solute is non-volatile, it is only the solvent molecules that are present in vapor phase, and they alone contribute to the vapor pressure. Let P1 be the vapor pressure of the solvent, Chi1 be its mole fraction, and P1 naught be its vapor pressure in the pure state. Then, according to Raoult's law, we can write P1 is directly proportional to Chi1. That is, vapor pressure of solvent is directly proportional to the mole fraction of the solvent itself. And we can write P1 is equal to Chi1 into P1 naught. The proportionality constant is equal to the vapor pressure of the pure solvent P1 naught. Now, if we plot a graph between vapor pressure and the mole fraction of the solvent, we will get a straight line passing through origin, that is, passing through 0. On the basis of Raoult's law, liquid and liquid solutions can be classified into two types: ideal solutions and non-ideal solutions. The solutions which obey Raoult's law over the entire range of concentrations are known as ideal solutions. These ideal solutions have two other important properties. One, the enthalpy of mixing of pure components to form the solution is 0. And second, the volume of mixing is also 0. That is, delta H of mixing is equal to 0 and delta V of mixing is equal to 0. What do we understand by telling delta H of mixing is equal to 0 and delta V of mixing is equal to 0? It means that no heat is absorbed or evolved when the components are mixed together. Also, the volume of solution would be equal to the sum of volume of the two components. Now, let us try to understand the ideal behavior of the solutions at molecular level by considering two components A and B. In pure component A, the intermolecular attractive interactions will be of the type AA, and in pure component B, the intermolecular attractive interactions will be of the type BB. Whereas in the binary solution of A and B, in addition to AA and BB type of interactions, we also see AB type of interactions. If the intermolecular attractive forces between AA and BB are nearly equal to those between AB type interactions, this leads to the formation of ideal solution. For example, if I speak of an ideal student, he or she should be obedient, punctual and honest, should always be focused on his or her studies, should be completing all the works in time, etc., etc. But do we find such a student with all these characteristics fulfilled? A perfectly ideal student is rare, isn't it? In the same way, a perfectly ideal solution is rare. But some solutions are nearly ideal in behavior. Solution of N-hexane and N-heptane, bromoethane and chloroethane, benzene and toluene, etc. are the examples to this category. Ideal solutions are the ones which obey Raoult's law over the entire range of concentrations, isn't it? So what are non-ideal solutions? Exactly, when a solution does not obey Raoult's law over the entire range of concentration, then it is called non-ideal solution. The vapor pressure of a non-ideal solution is either higher or lower than that predicted by Raoult's law. If the vapor pressure is higher, the solution exhibits positive deviation, and if the vapor pressure is lower than the expected from Raoult's law, the solution exhibits negative deviation from Raoult's law. The plots of vapor pressure as a function of mole fractions for positive and negative deviation from Raoult's law are shown in the figure here. The first graph represents a solution that shows positive deviation from Raoult's law, and the second graph represents a solution that shows negative deviation from Raoult's law. In both of these graphs, the dotted lines represents the vapor pressure that is predicted by Raoult's law, and the complete lines represents the vapor pressures exhibited by the solutions and the components present in it. Now the question is, when will a non-ideal solution have vapor pressure higher than that predicted by Raoult's law? And when will a non-ideal solution have vapor pressure lower than that predicted by Raoult's law? Thinking? You know that. You know the answer for this question. What is that? The cause for these deviations lies in the nature of interactions at the molecular level. In case of positive deviation from Raoult's law, AB interactions are weaker than those of AA or BB interactions. That is, in this case, the intermolecular attractive forces between solute-solvent molecules are weaker than those between solute-solute and solvent-solvent molecules. This means that in such solutions, the molecules of A or B will easily escape compared to its pure state. This will increase the vapor pressure and results in positive deviation. Mixtures of ethanol and acetone show positive deviation. In pure ethanol, molecules are hydrogen bonded. On adding acetone, its molecules get in between those of the alcohol molecules and break some of the hydrogen bonds present between the alcohol molecules. Due to the weakening of interactions, the solution shows positive deviation from Raoult's law. Another example is a solution formed by adding carbon disulfide to acetone. The dipolar interactions between solute-solvent molecules are weaker than the respective interactions among the solute-solute and solvent-solvent molecules. So this solution also shows positive deviation from Raoult's law. Now coming to the case of negative deviations. The intermolecular attractive forces between AA and BB are weaker than those between AB. This leads to decrease in vapor pressure resulting in negative deviations. An example of this type is a mixture of phenol and aniline. Here the intermolecular hydrogen bonding between phenolic proton and lone pair of nitrogen atom of aniline is stronger than the respective intermolecular hydrogen bonding between phenol-phenol and aniline-aniline. Another example is a mixture of chloroform and acetone. It forms a solution with negative deviation from Raoult's law. This is because chloroform molecules are able to form hydrogen bond with acetone molecule as shown in the figure. This hydrogen bonding between acetone and chloroform decreases the escaping tendency of molecules for each component in the solution, and as a result the vapor pressure decreases resulting in negative deviation from Raoult's law. Non-ideal solutions exhibit positive or negative deviation from Raoult's law. The solution which shows a large positive deviation from Raoult's law are also called minimum boiling azeotrope. The solutions that show large negative deviations from Raoult's law are also called maximum boiling azeotrope. What are these azeotropes? What is minimum boiling azeotrope? What is maximum boiling azeotrope? Azeotropes are binary mixtures having the same composition in liquid and vapor phase, and also they boil at a constant temperature. We cannot separate the components of an azeotrope by fractional distillation. We have two types of azeotropes called minimum boiling azeotrope and maximum boiling azeotrope. The solutions which show a large positive deviation from Raoult's law form minimum boiling azeotrope at a specific composition. Why the name is minimum boiling azeotrope? It is because when we plot constant pressure phase diagram for such a mixture, its temperature goes through a minimum. So it is called minimum boiling azeotrope. On the other hand, in the constant pressure phase diagram of maximum boiling azeotrope, temperature goes through a maximum. As told earlier, the solutions which shows a large negative deviation from Raoult's law form maximum boiling azeotrope at a specific composition. Just a few minutes before, you have learned that the vapor pressure of solution decreases when a non-volatile solute is added to volatile solvent. Many properties of solutions are connected with this decrease of vapor pressure, and these properties are relative lowering of vapor pressure of the solvent, depression of freezing point of the solvent, elevation of boiling point of the solvent, and osmotic pressure of the solution. All these properties depends on the number of solute particles irrespective of their nature relative to the total number of particles present in the solution. Such properties are called colligative properties. As an example, if I speak about the strength of students in a school, it depends only on the number of students studying in that school. Whether a student is a boy or a girl, whether the student is tall or short, does not affect the strength of the school. Strength of the school depends only on the number of students and it does not depend on the nature of students who are studying in that school. Now let us discuss colligative properties one by one, and we shall see how we can determine molar mass of the solute using these colligative properties. We have studied that the vapor pressure of a solvent in solution is less than that of pure solvent. Raoult told that the lowering of vapor pressure depends only on the concentration of the solute particles, and it is independent of the nature of the solute. Relation between vapor pressure of the solution, mole fraction and vapor pressure of the solvent is given by Raoult's law. That is, P1 is equal to chi1 into P1 naught. The decrease in the vapor pressure of the solvent is the difference between vapor pressure of the pure solvent and the vapor pressure of the solution. So the decrease in vapor pressure of the solvent is denoted by delta P1, that is given by delta P1 is equal to P1 naught minus P1. P1 naught can be written as P1 naught into chi1. So the expression is P1 naught minus P1 naught into chi1, which is equal to P1 naught into 1 minus chi1. We know that sum of mole fractions of the individual components is equal to 1, and therefore we can write chi2 is 1 minus chi1. So we can write delta P1 is equal to P1 naught into chi2. If the solution contains several non-volatile solutes, the lowering of vapor pressure depends on the sum of mole fractions of different solutes. Delta P1 divided by P1 naught is equal to P1 naught minus P1 divided by P1 naught, which is equal to chi2. Here the ratio delta P1 divided by P1 naught is called relative lowering of vapor pressure. It tells us how much decrease is observed in vapor pressure of the solution with respect to vapor pressure of pure solvent. We can write chi2 is equal to N2 divided by N1 plus N2. Here N1 and N2 are the number of moles of solvent and solute respectively which are present in the solution. So the expression for lowering of vapor pressure can be written as P1 naught minus P1 divided by P1 naught, which is equal to N2 divided by N1 plus N2. N1 and N2 are the number of moles of solvent and solute respectively which are present in the solution. For dilute solutions, the number of moles of solute is much less than the number of moles of solvent. That is, N2 is much lesser than N1. Hence, neglecting N2 in the denominator, we can write P1 naught minus P1 divided by P1 naught, which is equal to N2 divided by N1. We know that the number of moles is equal to mass of the component divided by its molar mass. That is, N is equal to W divided by M. So, we can write P1 naught minus P1 divided by P1 naught. That's equal to W2 into M1 divided by M2 into W1. Here, W1 and W2 are masses and M1 and M2 are molar masses of the solvent and solute respectively. It is using this equation, knowing all the other quantities, the molar mass of solute, that is M2, can be calculated. Vapor pressure of pure water at 298 Kelvin is 23.8 mm Hg. 50 gram of urea is dissolved in 850 gram of water. Calculate the vapor pressure of water for the solution and its relative lowering. So here we can make use of Raoult's law. So we have solute and solvent. So parameters related to solute, we shall represent it by subscript 2, and the parameters related to solvent, we shall represent it by subscript 1. So we are given with vapor pressure of pure water. Water is solvent. So vapor pressure is denoted by P1. So since it is for pure solvent, we'll write it as P1 naught, that is 23.8 mmHg. They have given 50 gram of urea is dissolved in 850 gram of water. We have weight of solvent, that's water, which is W1, 850 gram. Also they have given 50 gram of urea is dissolved, which is weight of solute, is equal to 50 gram. We need to calculate vapor pressure of water, that is P1. Also relative lowering of vapor pressure. Now let us write down the molar mass of water. Molar mass of water, which is a solvent. So therefore it is M1, that is 18 grams per mole. Molar mass of urea. Formula of urea is NH2CO NH2. 2 into atomic mass of nitrogen, that is 14, plus 1 into atomic mass of carbon, that's 12, plus 4 into atomic mass of hydrogen, which is 1, and also we have 1 oxygen, so 1 into 16. So this is equal to 28 plus 12 plus 4 plus 16, which is equal to 60 grams per mole. And from Raoult's law, we have P1 naught minus P1 divided by P1 naught, which is equal to W2 into M1 divided by W1 into M2. So let us substitute all the data into the expression of Raoult's law. We have P1 naught, which is 23.8 minus P1 is what we need to calculate, divided by P1 naught, that is 23.8, which is equal to W2, which is 50 grams, into M1, that is 18 grams per mole, divided by W1, which is 850 grams, into M2, which is 60 grams per mole. Let us simplify the right hand side part. So let me write left hand side part as such. 23.8 minus P1 divided by 23.8 is equal to 0.018. So from this we can write 23.8 minus P1 is equal to 0.018 into 23.8, and therefore P1 is equal to 23.8 minus 0.018 into 23.8. This is equal to 23.8 minus 0.42, which is equal to 23.38. The unit is mmHg. So this is the vapor pressure of water at the given temperature. They have also asked us to calculate the relative lowering in the vapor pressure. So this relative lowering is given by the expression on the left hand side of Raoult's law, which is equal to P1 naught minus P1 divided by P1 naught. So this is equal to P1 naught is 23.8 minus P1 is just now we have calculated, it is 23.38 divided by P1 naught, which is 23.8. This is equal to 0.42 divided by 23.8, which is equal to 0.0176. So therefore the relative lowering that is observed in the vapor pressure is 0.0176. You have studied in class 11 that the vapor pressure of a liquid increases with increase in temperature. The temperature at which vapor pressure of the solution is equal to the atmospheric pressure the liquid boils. For example, water boils at 373.15 Kelvin. that is 100 degrees Celsius. Because at this temperature, the vapor pressure of water is 1.013 bar, that is 1 atmosphere. Also, we know that vapor pressure of the solvent decreases in the presence of non-volatile solute. The graph here shows the variation of vapor pressure of pure solvent and solution as a function of temperature. From this graph, we can see that the boiling temperature for solution is more than that of the pure solvent. Why this is happening? For example, the vapor pressure of an aqueous solution of sucrose is less than 1.013 bar at 373.15 Kelvin, that is 100 degree centigrade. Now, in order to make the solution of sucrose boil, we should increase its vapor pressure to 1.013 bar by rising the temperature above the boiling temperature of pure solvent, that is water. Therefore, boiling point of solution is always higher than that of the boiling point of the pure solvent in which the solution is prepared, as shown in the graph. The elevation of boiling point also depends on the number of solute molecules rather than their nature, similar to the lowering of vapor pressure. A solution of 1 mole of sucrose in 1000 grams of water boils at 373.52 Kelvin at 1 atmospheric pressure. Let Tb0 be the boiling point of pure solvent, and let us consider Tb as the boiling point of the solution. The increase in the boiling point, delta Tb, is equal to Tb minus Tb0. This is known as elevation of boiling point. Experiments have shown that for dilute solutions, the elevation of boiling point is directly proportional to the molar concentration of the solute in the solution. That is, delta Tb is directly proportional to m, or we can write delta Tb is equal to Kb into m. Here, m is molality. It is the number of moles of solute dissolved in 1 kg of the solvent. And the constant of proportionality Kb is called boiling point elevation constant or molar elevation constant. It is also called as ebullioscopic constant. The SI unit of boiling point elevation constant Kb is Kelvin kg per mole. Now, if W2 gram of solute of molar mass M2 is dissolved in W1 gram of solvent, then molality of the solution is given by M is equal to W2 divided by M2 divided by W1 by 1000, which is equal to 1000 into W2 divided by M2 into W1. Substituting the value of molality into the expression of elevation of boiling point, we can write delta Tb is equal to Kb into 1000 into W2 divided by M2 into W1. Rearranging this expression, we can write M2 is equal to Kb into 1000 into W2 divided by delta Tb into W1. Thus, by knowing the quantities W1, W2, delta Tb along with the molar elevation constant Kb, we can determine the molar mass of the solute. On dissolving 2.34 gram of solute in 40 gram of benzene, the boiling point of solution was higher than that of benzene by 0.81 Kelvin. Kb value for benzene is 2.53 Kelvin kg per mole. Calculate molar mass of the solute. So they have given that on dissolving 2.34 gram of solute in 40 gram of benzene. So 40 gram is weight of benzene, which is solvent. So therefore it is represented as W1, and weight of solute is represented as W2, which is 2.34 gram. So they told that boiling point of solution was higher than benzene by 0.81 Kelvin. Means we observe an increase in the boiling point, which is elevation in boiling point, represented as delta TB, which is equal to 0.81 Kelvin. So they have given us the value of Kb for benzene, which is 2.53 Kelvin kg per mole. And we need to calculate molar mass of this solute, that is M2. So we have the formula from the elevation and boiling point. The molar mass of solute M2 is equal to Kb into W2 into 1000 divided by delta TB into W1. Substituting all the values into the formula, Kb is 2.53 into W2 is 2.34 into 1000 divided by delta TB, which was 0.81 into W1, that is 40. After simplifying this, we will get the molecular mass M2 is 182.72 gram per mole. So therefore, the molar mass of solute is 182.72 gram per mole. The lowering of vapor pressure of a solution causes lowering of the freezing point compared to that of pure solvent, represented by the graph here. Freezing point of a substance is defined as the temperature at which vapor pressure of the substance in its liquid phase is equal to vapor pressure in the solid phase. At the freezing point of a substance, the solid phase is in dynamic equilibrium with the liquid phase. A solution will freeze when its vapor pressure equals to the vapor pressure of pure solid solvent. According to Raoult's law, when a non-volatile solid is added to the solvent, its vapor pressure decreases, and at a lower temperature, vapor pressure of liquid phase will become equal to that of solid solvent, and therefore the freezing point of the solvent decreases. If we consider Tf0 as the freezing point of pure solvent and Tf as a freezing point when non-volatile solute is dissolved in the solvent, the decrease in freezing point is delta Tf is equal to Tf0 minus Tf. This is known as depression in freezing point. Similar to the elevation of boiling point, the depression of freezing point delta Tf for dilute solution is directly proportional to molality of the solution. Thus, we have delta Tf directly proportional to m, or we can write delta Tf is equal to Kf into m. The proportionality constant Kf, which depends on the nature of solvent, it is known as freezing point depression constant or molar depression constant, or it is also called as cryoscopic constant. The SI unit of cryoscopic constant is Kelvin kg per mole. If W2 gram of solute having molar mass M2 present in W1 gram of solvent, it produces the depression in freezing point delta Tf of the solvent. Then the molarity of the solution is written as M is equal to W2 divided by M2 divided by W1 by 1000, which is equal to 1000 into W2 divided by M2 into W1. Substituting the value of molality into the expression of depression of freezing point, we can write delta Tf is equal to Kf into 1000 into W2 divided by M2 into W1. Rearranging this expression, we can write M2 is equal to Kf into 1000 into W2 divided by delta Tf into W1. Thus, by knowing the quantities W1, W2, delta Tf along with the molar freezing point depression constant Kf, we can determine the molar mass of the solute. The values of Kf and Kb, which depends only on the nature of solute, can be ascertained from the following relations. Kf is equal to R into M1 into Tf divided by 1000 into delta H fusion. Kb is equal to R into M1 into Tb2 divided by 1000 into delta H of vaporization. Here the symbols R and M1 stands for the gas constant and molar mass of the solvent, and Tf and Tb denotes the freezing point and boiling point of the pure solvent. It is written in terms of Kelvin. Delta H of fusion and delta H of vaporization represents the enthalpies for fusion and vaporization of the solvent. Addition of 0.643 gram of compound to 50 ml of benzene with the density 0.879 gram per mole lowers the freezing point from 5.15 degrees centigrade to 5.03 degrees centigrade. If Kf for benzene is 5.12 Kelvin kg per mole, calculate the molar mass of the compound. They have given us mass of compound which we add to benzene. So this compound is solute. So its mass is written as W2, which is 0.643 grams. They have given 50 ml of benzene, and so volume of benzene is given, which is equal to 50 ml. Also they have given us density. So density of benzene is equal to 0.879 gram per ml. Using the volume and density, we can calculate mass of benzene. So therefore we have mass of benzene, which is its volume multiplied with density. That is equal to 50 ml into 0.879 gram per ml. That's equal to 43.95 gram. So this mass of benzene is represented as W1. They told that the freezing point is lowering from 5.15 degrees centigrade to 5.03 degrees centigrade. So we observe depression in freezing point, that is represented as delta Tf, which is equal to 5.15 minus 5.03, which is equal to 0.12. This difference can be written in terms of Kelvin, that is 0.12 Kelvin. Kf value is given, which is 5.12 Kelvin kg per mole. So we know that depression in the freezing point delta Tf is equal to Kf into molality M. So the formula can be written as delta Tf is equal to Kf into W2 into 1000 divided by M2 into W1. Substituting all the values into the formula, delta Tf is 0.12, which is equal to Kf is 5.12 into W2 is 0.643 into 1000 divided by M2 is what we have to calculate, which is the molar mass of the compound that's added. W1 is 43.95. So therefore, we can write M2 is equal to 5.12 into 0.643 into 1000 divided by 0.12 into 43.95. So now let's simplify this. After simplification, we get M2 as 624.22 gram per mole, which is the molar mass of the compound that's added, which decreases the freezing point of the benzene. We observe raw mangoes shrivel when pickled in salt water, and wilted flowers revive when placed in fresh water. Blood cells collapse when suspended in saline water, etc. In all these processes, we find one thing in common. That is, all these substances are bound by membranes. These membranes can be of animal or vegetable origin, and these membranes occur naturally, such as pig's bladder or parchment, or it can be synthetic, such as cellophane. These membranes are continuous sheets or films. They contain a network of submicroscopic holes or pores. Small solvent molecules like water when pass through these holes, but the passage of bigger molecules like solute cannot pass through. Membranes having this kind of properties are known as semi-permeable membranes. In short, they are known as SPM. Let us assume that only solvent molecules can pass through these semi-permeable membranes if this membrane is placed between solvent and solution. You can visualize this from the figure here. The solvent molecules will flow through the membrane from pure solvent to the solution. This process of flow of solvent is called as osmosis. So, when the solvent molecules flow through the semi-permeable membrane from pure solvent to the solution side, we call the process as osmosis. Now, the question is, how long this process will continue? The flow will continue till the equilibrium is reached. Now, if some extra pressure is applied on the solution, we can stop the flow of the solvent from its side to the solution side across the semi-permeable membrane. This pressure that just stops the flow of solvent is called as osmotic pressure of the solution. So, it is the pressure that just stops the flow of solvent from the pure solvent to the solution side. That is what we call as osmotic pressure of the solution. The flow of solvent from dilute solution to the concentrated solution across the semi-permeable membrane is because of the osmosis. It is important to keep in mind that solvent molecules always flow from lower concentration to higher concentration of the solution. The osmotic pressure has been found to be dependent on the concentration of the solution. Observe the diagram here. We have a solution and its pure solvent separated by a semi-permeable membrane. Solvent molecules will pass through the solution side through the semi-permeable membrane. To stop this flow of solvent, we have to apply some extra pressure on the solution side. The osmotic pressure of a solution is the excess pressure that must be applied to a solution to stop the passage of solvent molecules through a semi-permeable membrane into the solution. That is, to prevent the osmosis, we should be applying some extra pressure. Osmotic pressure depends on the number of solute molecules and do not depend on the identity of the solute particles. So, osmotic pressure is a colligative property. And for dilute solutions, osmotic pressure is proportional to molarity of the solution at a given temperature. It's molarity and not molality. The previously learnt colligative property were directly proportional to molality of the solution, but here the osmotic pressure is directly proportional to molarity of the solution. So, we can write pi is equal to CRT, where pi is the osmotic pressure, C is concentration, R is gas constant, T is temperature. And we can write pi is equal to N2 divided by V into RT, where V is volume of the solution in liters containing N2 moles of the solute. If W2 gram of solute of molar mass M2 is present in the solution, then number of moles N2 is equal to W2 divided by M2. And therefore, we can write pi into V is equal to W2 into RT divided by M2. Or rearranging this equation, I can write M2 is equal to W2 into R into T divided by pi into V. So, by knowing the quantities W2, T, osmotic pressure pi and volume V, we can calculate the molar mass of the solute. This method of measurement of molar mass of solute is widely used to determine molar masses of proteins, polymers and other macromolecules. This method has advantage over the other methods which we have discussed. Now, let us see what are the advantages of osmotic pressure measurements over the other measurements. This pressure measurement is around the room temperature and the molarity of the solution is used instead of molality. As compared to the other colligative properties, the magnitude of osmotic pressure is large even for very dilute solutions. This technique is particularly useful for determination of molar mass of biomolecules, as they are generally not stable at higher temperatures. If we have two solutions at a given temperature having same osmotic pressure are called isotonic solutions. When we place isotonic solutions separated by a semi-permeable membrane, osmosis will not occur between them. For example, the osmotic pressure associated with fluid inside the blood cell is equivalent to that of 0.9% mass by volume sodium chloride solution. 0.9% mass by volume sodium chloride solution is called normal saline solution and it is safe to inject intravenously. On the other hand, if we place the cells in a solution containing more than 0.9% mass by volume sodium chloride, water will flow out of the cells and they would shrink. Such a solution is called as hypertonic solution. If the salt concentration is less than 0.9% mass by volume, the solution is said to be hypotonic. If cells are placed in this solution, they would swell because water will flow into the cells. Calculate the osmotic pressure of 5% solution of cane sugar, which is sucrose with the formula C12H22O11 at 15 degree centigrade. So we have the formula osmotic pressure pi is equal to W2 into R into T divided by M2 into V. So from the question, they have given us 5% solution of cane sugar, which means that we have 5 gram of sucrose in 100 gram of water or 100 ml of water. So I can write weight W2 of sucrose, which is 5 gram, and the value of R is 0.0821 liter atmosphere per Kelvin per mole. So temperature they have given us as 15 degree centigrade, which is equal to 15 plus 273 Kelvin, that's equal to 288 Kelvin. And we need molar mass of solute, that is sucrose, which is 12 into atomic mass of carbon, that's 12, plus 22 into atomic mass of hydrogen and 11 into atomic mass of oxygen. So we have molar mass M2 is equal to 342 grams per mole. Also they have given us volume of the solution, which is 100 ml. So when we convert this into liter, that comes out to be 0.1 liter. Now let's substitute all these things into the expression for osmotic pressure. So therefore, osmotic pressure pi is equal to W2, that's 5, into R is 0.0821 into T, which is 288, divided by M2, which is 342, and volume that is 0.1 in terms of liter. After simplifying this, we get the osmotic pressure of the solution as 3.457 atmosphere. The natural phenomena which I spoke when I began this topic can be explained based on osmosis. A raw mango placed in concentrated salt solution, it loses water via osmosis to shrivel into pickle. Wilted flowers, they get back the water when it is placed in fresh water. A carrot that has become limp because of water loss into the atmosphere, we can place it in water to make it firm once again. Water will move into the carrot through osmosis. When placed in water containing less than 0.9% mass by volume salt, blood cells swell due to flow of water into the blood cells because of osmosis. People who are taking lot of salt or salty food experience water retention in tissue cells and intercellular spaces because of osmosis, and this results in puffiness or swelling. This is called as edema. Water movement from soil into plant roots and to the upper portion of the plant is also partly due to osmosis. Meat is preserved from bacterial action by adding salt, and fruits are preserved by adding sugar. Through the process of osmosis, a bacterium on the salted meat or candied fruits loses water, shrivels and dies. So this is how we can preserve meat. We can reverse the direction of osmosis if we apply a pressure larger than the osmotic pressure to the solution side. Now the pure solvent which flows out of the solution through the semi-permeable membrane. This phenomenon is called reverse osmosis. Reverse osmosis has great practical utility. Reverse osmosis is used in desalination of seawater. A schematic setup for the desalination process of water is shown here. When pressure more than osmotic pressure is applied, pure water is squeezed out of the seawater through the membrane. A variety of polymer membranes are available for this purpose. The pressure required for the reverse osmosis is quite high. Porous membranes that can be used is a film of cellulose acetate placed over a suitable support. Cellulose acetate is permeable to water but impermeable to impurities and ions present in seawater. To meet potable water requirements, many countries use desalination plants nowadays. Now, let us discuss about the abnormality in molar masses. What is abnormal molar mass? Molar mass that is either lower or higher than the expected or normal value is called as abnormal molar mass. For example, let us consider ethanoic acid, that is acetic acid. When taken in benzene, ethanoic acid dimerizes due to hydrogen bonding. So, the number of particles is reduced due to dimerization. So, we observe a change in molar mass than that is expected. Van Hoff introduced a factor I, which is known as Van Hoff's factor, to account for the extent of dissociation or association. So, this factor I is defined as I is equal to normal molar mass divided by abnormal molar mass, or I is equal to observed colligative property divided by calculated colligative property, or I is equal to total number of moles of particles after association or dissociation divided by the number of moles of particles before association or dissociation. Here, abnormal molar mass is the experimentally determined molar mass, and calculated colligative properties are obtained by assuming that non-volatile solute is neither associated nor dissociated. In case of association, the value of I is less than unity, while for dissociation the value of I is greater than unity. Now, including this Van 't Hoff factor, we can modify the equations for colligative properties. Relative lowering of vapor pressure of solvent is written as delta P divided by P1 naught, which is equal to I into Chi2. That is, P1 naught minus P1 divided by P1 naught is equal to I into N2 divided by N1. Elevation of boiling point delta TB is equal to I into KB into M. Depression of freezing point delta TF is equal to I into Kf into M. In the same way, osmotic pressure of the solution is equal to I into N2 into RT divided by V. The freezing point of a solution containing 0.3 gram of acetic acid in 30 gram of benzene is lowered by 0.45 degrees Celsius. Calculate the Van 't Hoff factor. Kf for benzene is 5.12 Kelvin kg per mole. Let's list the things that's given. So the total solution is containing 0.3 gram of acetic acid. So acetic acid is solute here. Therefore, W2 is the mass of acetic acid, which is solute. It is 0.3 gram. We have 30 gram of benzene. So benzene is solvent. Its mass is represented as W1. So W1 is equal to 30 gram. So they observed that freezing point was lowered by 0.45 degree centigrade. This is also equal to 0.45 Kelvin. So this is the depression in the freezing point, which is delta TF. Also they have given us the value of Kf for benzene, which is 5.12 Kelvin kg per mole. So now we have the formula. The molar mass of solute M2 is equal to Kf into W2 into 1000 divided by delta TF into W1. Substituting, Kf is 5.12 into W2 is 0.3 into 1000 divided by delta TF, which is 0.45 Kelvin, into W1, which is 30. So after simplifying this, we find that molar mass of the solute is 113.8 gram per mole. So this is the experimental molar mass, but the normal molar mass of the solute, which is acetic acid here, that's formula is CH3COOH. So this is equal to 2 into atomic mass of carbon, that's 12, plus 4 into atomic mass of hydrogen, 1, plus 2 into atomic mass of oxygen. So we have 24 plus 4 plus 16 into 2, that's 32, which is equal to 60 grams per mole. So we observe there is a change in molar mass of acetic acid in the experimental value. So we need to calculate Van 't Hoff factor, which is I, that is the ratio of normal molar mass to the observed molar mass, which is calculated by the experimental value. So that is observed molar mass. So substituting into this formula, we have normal molar mass, which is 60 grams per mole. But experimentally we observed that mass of acetic acid is 113.8 grams per mole. So the unit gets cancelled. 60 divided by 113.8 is equal to 0.53. And therefore the Van 't Hoff factor is 0.53. In this video, we have studied Solutions chapter from class 12 chemistry. If you haven't watched our other NCERT classes, you can watch them by clicking on the playlist appearing here. Thank you for watching. Stay connected, keep learning. Take care. Bye-bye.